Okay, so let's look at some oxidation reduction reactions, or more commonly known as redox reactions. So these types of reactions, of course, where the oxidative state of species change. So you'll notice, most reactions are actually oxidation reduction reactions, and it should be quite easy to recognize them, but that's what we will look at. We'll look at some of the terminology that we need to use. So we start by looking at a common example. So iron oxide, iron trioxide, solid, reacts with CO, carbon monoxide, gas, to form iron, so solid iron plus carbon dioxide. And of course, you should be able to do the balancing. Shouldn't be too difficult. Now the question is this an oxidation-reduction reaction? And the only way to check that is, or the easiest way to check that is to see if the iron undergoes a change in its oxidation number. So the oxidation number in iron here is of course 3+, and the oxidation number of iron here is 0. So yes, indeed, there is something that happens. It needs to go from +3 to 0, so it means it must gain electrons, because, to go from +3 to 0, you need to -3. So that means at least 3 electrons need to be absorbed by it. And hence, it is then an oxidation-reduction reaction. But we know we have certain terminology that we need to use. So, for example, one of the species in an oxidation-reduction reaction, exactly why it's called a redox reaction, if one thing undergoes oxidation, something else needs to undergo reduction, or vice versa. So we start with this one. So we say the iron gains electrons, You can also say that it loses oxygen. So that's another way to know. It lost oxygen. It went from O3 to just iron. And in other words, it must have been reduced. So it is what we call reduced. It means the oxidation number reduces. And remember, to go from -1 to -2 also means you reduce the number. But if something is oxidized, something else, if something is reduced, something else must be oxidized. So the only other thing that can undergo that is the carbon monoxide, and you actually see it goes from carbon monoxide to carbon dioxide. So it gains oxygen. So in other words, CO, it gains oxygen, and it will need to give electrons for the iron to gain electrons. In other words, it loses electrons. And in that process, it forms a bond with oxygen. So in other words, this one is oxidized. Right. Other terminology that I want to introduce is the thing that is being reduced. We call it the oxidizing agent. And the thing that's being oxidized is called the reducing agent. Okay, and we will look at the definitions down here, so you can check them there as well. So that's the basic idea of a redox reaction. You know, something that's oxidized, something that's reduced, something that gains electrons, something that loses electrons. The concept of gaining and losing oxygen is not necessarily connected to redox reactions, you can have reactions where there's no oxygen and it still has a reduction and oxidation taking place. Another common example is one where you have magnesium, solid magnesium, and you burn it in oxygen, which then produces magnesium oxide, which is a solid. So again, we need to ask ourselves what's happening to the magnesium. So magnesium is here in the 0th oxidative state, and here it must be in the +2 oxidative state, because why? Oxygen always has a 2- charge, so it always has an oxidative state of -2. There's an exception, but it's there. So we can also, and we also write of molecular oxygen's oxidative state is also 0. So we can clearly see which one is gaining electrons. The magnesium is gaining electrons and the oxygen is losing electrons. So we can also look at in the concept, let me just correct that first. Magnesium is losing electrons and oxygen is gaining electrons. I misspoke. Because the magnesium goes from 0 to +2. So the only way that you can get to +2 is if you lose 2 charges. And those electrons are then absorbed by the oxygen. You could also say magnesium here forms a bond with oxygen. So in other words, it is oxidized. So magnesium is oxidized, that makes it the reducing agent. Oxygen is reduced, in other words, it is the oxidizing agent. But as I mentioned, not all reactions contain oxygen. So we need to look where the electrons go as the main point. Here I just give you some definitions. So the substance that accepts electrons is reduced. The substance that loses electrons is oxidized. The reducing agent is oxidized. The oxidation agent is reduced. So the colors match each other there, so you can always remember that. Let's look at an oxidation reaction. It says aluminium reacts with oxygen to produce aluminium oxide. And it says which species is oxidized, which is reduced. Identify the oxidizing agent and the reducing agent. So in principle, what do we need to do? We just need to check oxidative states. So both of these go from 0, and this one goes then to +3, and oxygen is -2. So, you use the -2 of the oxygen to determine what the oxidative state of the aluminium is. So, aluminium loses electrons. In other words, it is oxidized. And if it's oxidized, it makes it the reducing agent. Oxygen, on the other hand, O2, it gains electrons. So that means it is reduced. Remember, it means the number is reduced. Never made sense to me why we say when something gains electrons, it's reduced. But it's because of the number that goes lower. It goes from 0 to -2. And that makes it, of course, if it's reduced, it makes it the oxidizing reagent. Right. I summarized some of the details here for you. You can go check that. So it's exactly what we've just done. And it's just all summative for you. Now, we've already used the concept of oxidation numbers. So in other words, what we were using is we said aluminium in the 0+ state goes to aluminium in the 3+ state, for example, in the previous example. We sometimes also write it as aluminium, let's say, or aluminium with a Roman numeral 3. That's there. Right. So some general rules for assigning it. Atoms in pure elements has an oxidative number of 0, so that's like iron 0, or aluminium 0. For monoatomic ions, the oxidative number is equal to the charge on the ion, so let's say it's 2 minus, so then it means it's minus 2. When something is combined with fluorine, or when combined with another element, then fluorine has an oxidation number of -1. Why? Because it's the most electronegative species on the periodic table. So it will have a -1 charge, it will carry a -1. And then the oxidation number of oxygen is always -2, or in most compounds, except when it is combined with fluorine. So when it's combined with fluorine, so in other words, if you have FO, not that that exists, but the fluorine then has to have a charge of -1. So in other words, the oxygen needs to have a +1 charge. And then in things called peroxides or superperoxide, then it can have a smaller, or meaning it might have a non-integer oxidative number, so like -0.5 or -1, depending. So for example, it has -0.5 in potassium oxide here, and it will have -1 in the sodium oxide there. So things that you need to be aware of. Things like chlorine, bromine, iodine have oxidative numbers of -1 in compounds, except when combined with oxygen and fluorine. So in this case, oxygen will dominate again and fluorine will dominate. So in other words, the chlorine, bromine, and iodine, always -1, except when with oxygen and fluorine. So then you need to balance oxygen. So you get like BRO, then you know, or not that you will you get like a BRF, but anyway. Hydrogen is +1, most compounds, like nearly all of them. And then we must get the algebraic sum of all the oxidative numbers of each species in a compound needs to be 0, depending on, or if the ion has a charge, it must equal to the charge. So what does that mean? Well, let's look at this example. So we want to determine what the oxidative state of aluminium is in this compound, so aluminium trioxide. What is the overall charge of this species? The overall charge of the species is 0. So 0 is equal then to, we want to determine aluminium, so a way that I would like to write it is in this way. It's a bit of a funny notation, but I think you'll get the idea. Plus 3 times O2 minus. So we then write that. So overall charge is 0 because there's no charge in the compound. And that must be equal to twice the charge of the aluminium plus 3 times the charge of the oxygen. So this is 2x plus 3 times -2. Still 0. So x is then equal to, so this becomes -6. We take 6 across the equation, or across the equal sign, you get 6 divided by 2. So that gives us +3. So now you can always use that check. Interestingly, just on a different note, you know why something changes sign when you take it across the equal sign? It's because in principle what you're doing is you're saying +6. How do you get rid of the 6? You have to say +6, and then you do it on both sides. So then you get 0 on the right hand side and you get 6 on the other. Okay, that's something completely else. So the B question, it says phosphorus and phosphoric acid. So again, what is our overall charge? Our overall charge is 0. So 0 must be equal to 3 times the charge on hydrogen plus the charge on phosphorus plus 4 times the charge on oxygen, which is always 2 minus. Therefore, 0 is equal to 3 plus x plus 4 times minus 2. You can make that 3 minus 8 plus x, because 4 times minus 2 is 8. So we get minus 5. Take it across the equation. Take it to the other side. So x must be equal to plus 5. And I specify the pluses here, so plus 3 and plus 5, because sometimes it's more, you can't be ever too explicit when writing your numbers. So 3 it implies it's positive, but it not necessarily. It could be just a typing mistake. But if you say plus 3, then everyone knows, okay, definitely that. Also, just something I thought of that we could add is, so we can say it means this is aluminium 3 plus, or it's aluminium 3, Roman numeral 3. And this one means it's phosphor 5 plus, or V. Okay. The next compound is, well, not compound, it's the sulfate ion. We want to know what this charge is, what the oxidative number is of the sulfur. So what is the overall charge of the species here? The overall charge of the species is minus 2. So now it means minus 2 needs to be equal to the charge on sulfur plus 4 times the charge on oxygen. So that means it's x minus 8. And we take minus 8 to that side. It becomes plus 8. So 8 minus 2, it means x is equal to plus 6. So we have sulfur Vi, or sulfur 6 plus. So we're at our final one. We're looking for the chromium atom in the dichromate ion. So again, the overall charge is minus 2. 2 times chromium X plus 7 times oxygen 2 minus is equal to 2x plus 7 times minus 2. It means minus 14. On the other side becomes plus 14. 14 minus 2 is 12. So x is equal to 12 over 2, and that is plus 6. So we have chromium 6 plus chromium Vi. Okay, that's essentially where I wanted to get to in this video. I hope it assists you and that you are well versed in getting oxidation numbers. In the next phase, we will then look at recognizing oxidation-reduction reactions and looking at how to balance oxidation-reduction reactions in different kind of media. All right, thank you for watching.